Thank you very much, Christian. Thank you all. Thanks to the organizers for the kind invitation to speak here today also. When we wrote the abstract, we were quite excited about the newest results, which is what you see on the left here, these threads. And in the meantime, we have done quite some part on the earlier part, which was the cholesteric liquid crystal elastomer sheets, which you see on the right. So in the end, I decided to talk about both because there are some nice, interesting developments on both these. And I decided to change the title a little bit to simply speak about why cholesteric liquid crystal elastomers are really useful in ways that you may not immediately think about, whether they are in form of threads or in sheets. So before starting, I wanted to mention the two people who have done most of the work. It's the two postdocs. Jon Gunn is the physicist, and Rijesh Kiratadat is the chemist. And the funding comes from ERC. And I would like to dedicate this talk to two people who have meant a lot for me. Wojtek Kuczynski was actually my first contact with the Polish Liquid Crystal Society. And I have very fond memories of my time in Poznan. I think I met Alexei Buglo there for the first time also. Wojtek has really been an inspiration in many ways. And Bengt Stabler, maybe not so many of you know him, but he was my PhD advisor and one of the co-founders of the Liquid Crystal Group in Gothenburg. He passed away last week, unfortunately. So let me start then to explain a little bit about my new title, so to speak. Why would cholesteric liquid crystal elastomers be useful? And I would like to bring your attention to an area where you probably have never thought of using liquid crystal at all. And that is in big stuff, infrastructure, the built environment. This is a Wired report from 2015, when Obama still was president. And you notice that they point out that it's time to fix America's infrastructure. There's some really serious issues. You might think that in 2021 things would look better, but this is from 2021, and it's not so much better. This is just from 2 days ago. I took the screenshot from the website of the American Society for Civil Engineers. And the scorecard, they do a scorecard like in school, for America's infrastructure has increased. It is now up to C-. Now, if you think that is a good thing, still C-, as you all remember from school, is not a very good grade. So the infrastructure is indeed in a pretty bad shape. And it's not just infrastructure, it's built environment in general. I think we all remember this. This was earlier this year in Florida, where suddenly half of the inhabitants found the other half was missing, and that half was the one who were lucky, because more than 90 people died in that. So is it just America? No, of course not. This was Genoa in Italy, Ponte Morandi in 2018. Europe has its share of infrastructure problems as well, as does the whole world. So there is a significant activity in monitoring the health of our infrastructure, our built environment in general. So the field is called structural health monitoring, and as you can see in this overview, it's based on basically putting in sensors and gauges and so on in the infrastructure. And I just highlight a few: the strain gauge, crack meter, and displacement sensor, because these are the ones where liquid crystal elastomers can be really useful. But how is it done today? Well, the typical thing you use today, this is from the same website that I took the previous picture, is you put in these types of sensors. They are often fiber optical, some are electrical, piezoelectric. And the key thing with these gauges is that they give a single value per sensor. There we go. So one gauge, one value. And that means that your resolution isn't that great. And that can be a problem in many respects. And that's something that this article here highlights. They talk about large area strain sensing. and they point out damage significantly influences response of a strain sensor only if it occurs in the proximity of the sensor. Therefore, two-dimensional sensing sheets covering large areas of a reliably early-stage damage detection for structural health monitoring applications is necessary. So the point is, if you have these one sensor, one value sensors, you can have a crack developing right next to the sensor, and the sensor will report nothing. So they, in this paper, they suggest a quite complex array of resistors to have an area detection of strain. But of course, if you think about the movie I showed in the beginning, cholesteric liquid crystal elastomers do that all by themselves. That's what they do. And you notice maybe that the colors here are different in different parts of the sheet. Maybe you think that this is because of imperfections, but that's not the case. Here's another movie where we deliberately blocked half of the sheet so it doesn't deform at all, and you see that the color remains. And of course it works in compressive strain as well. Here, it's awkward with the phone while with the microphone. So here is in compressive strain, and you see it detects exactly where you apply the pressure. So cholesteric liquid crystal elastomer sheets are 2D continuous strain sensors with an immediate visible response that the human eye can see or a camera can see. And that is very, very useful. And I should remind you, these can be made very large. The largest we made for that paper were 35 square centimeters. And there's no limit to that. Or no obvious limit to that. So this is again from the page that I quoted before, some of the benefits of SHM for new infrastructure that is being built, and you saw that there is a major incentive to build new infrastructure. There is a need to improve things. There is now more and more incentives to build in sensors from the very beginning. And you may have heard of Industry 4.0 and Internet of Things. It's all related to this. Anything that is being constructed nowadays comes with sensing elements. And most of them are, of course, electronic, which is convenient in many respects, but electronics need cables or power supplies or batteries. The cholesteric liquid crystal elastomer needs nothing. It is what it is. It runs on thermal energy. You just need something to observe it, which is quite interesting. Of course, older infrastructure that already exists can also benefit from sensors being installed in terms of increasing lifespan and, of course, trust among the people who use them. And you can have real-time alarms that detect whether there is a serious issue coming up. So how would you do this with the cholesteric liquid crystal elastomer? Well, you would mount these sheets on the structures. So these are rubbers, so the strains of a couple of, about 20% is required to see a color response. You may think, well, concrete would rupture after 1%, far before that, it's not straining. But the point is that even healthy concrete has cracks. Good concrete, as it should, it has cracks. The danger is when those cracks expand. So you can easily a crack expansion of 100% is still okay, but it suggests that something is serious. So if you cover the concrete with the cholesteric liquid crystal elastomer, the CLCE would show where a crack is expanding quite easily. It's perfectly in the right range. And of course, you could then use a webcam or similar to monitor the color if you don't have people doing it. And for high-rise building, well, you can easily use drones. They all come with cameras and lights. It's actually not only interesting for healthy infrastructure, only interesting for infrastructure that is failing. Also for healthy infrastructure, it is of interest. So there have been a couple of accidents that happen all the time, where perfectly healthy infrastructure collapses because of overcrowding, for instance. This was quite recently on the West Bank, where 2 people died because of seats collapsing. This is not too far away from here, in Katowice, 2006. There was snow on the roof, and the weight of the snow was so great that the roof caved in and more than 60 people died. And this is from Stockholm during an Avicii concert. People were jumping in synchrony, and the false floor collapsed. Luckily, nobody died, but some 25 people were injured. So, of course, you can put up sensors of these types that then monitor in real time, for instance, during a concert, if the false floor is approaching a situation where a dangerous situation can arise. And this is a beautiful example of what you can do with cholesteric liquid crystal elastomer from Lawrence DeHaan's group in Guangzhou. They made it so it reflected in the infrared originally, so it was transparent. And then when you strain it, the color changes and the pitch, there's a redshift. I thought this would be repeating. And you see a red warning triangle coming out from that. So very elegant, also showing that you can even structure these to make patterns available. So I'm working a lot with a colleague called Matthew Schwartz. He is an expert in the built environment, and we published an article on Archive. So if you're interested in this, I can recommend this. We discussed this type of effect, for instance, for a window during a hurricane that could alert if the wind is dangerously strong, or a glass ceiling, for instance, against snowfall and so on, where you would normally not see anything because the CLC is transparent, but under too strong glow, suddenly color comes out and warns you of it. So how does this all work? A little primer for, especially with the younger among you who maybe don't know exactly why these colors arise, and maybe even there are some others who don't know. So a brief introduction to chiral nematics or cholesterics. It's a nematic phase, there's no long-range positional order, but it's chiral, so the director is being modulated in a helical fashion. Very often it's drawn like this. I would like to point out that this is a schematic. There are no layers in a cholesteric. It's really a nematic in the sense that there is no position order. It's a director field that is being drawn here, not the molecules themselves. So it's not a layered phase. This is maybe a slightly more realistic depiction of what the cholesteric phase might look like if it's made from rods. This is what it might look like if it's made from discs. And here, just for simplicity, I made the pitch very, very tightly exaggerated, just so you see the whole modulation. This is maybe a better drawing that we made for another paper that shows you the director helix, and it shows something that maybe not everyone thinks about. When you think about a helix, you often think about a spring, right? That is continuous, like the red part here. So we often think that the helix, if you follow the director, you will go up along the helix. That's actually not the case. The director is perpendicular to the helix everywhere. That is indeed the definition of the cholesteric helix. So it's an unusual helix in the sense that the structural elements of the helix, so to speak, are never along the helix axis. So it's the end of the director, that I drew here as the red circle, that traces the kind of traditional helix, but the actual director is perpendicular to the helix. That's important to remember. And I also want to mention that often you make a cholesteric by inducing the chirality by mixing in a chiral with a non-chiralose phase. That's what we do here also. So what about the optical properties? Well, if you have a helical modulation, and Christian already alluded to it earlier, you are modulating the optical properties because the refractive index along and perpendicular to the director are different, and now the director is rotating, so you have a periodic modulation of the optical properties of the refractive index. So you actually have multiple types of optical effects arising from this, and what you see depends first of all on the ratio between the pitch and the wavelength of light within the liquid crystal. So the one that we're dealing with here is selective reflection. That's what gives rise to the color. It's a kind of Bragg reflection, and it happens to circularly polarized light that has the same handedness as the helix if it's undistorted. And it happens around a bandwidth where the wavelength is the same as the pitch, the wavelength again in the liquid crystal. So that means that if your pitch is in the range of about 300 to 400 something nanometers, then you get colorful selective reflection. So because the refractive index is on the order of, average refractive index is on the order of 1.5. Now, if the light propagates perpendicular to the helix, then you don't see any selective reflection at all. Instead, you just see birefringence. And if you have intermediate angles, we have a color shift, you have a blue shift of the reflection, and you can have birefringence for what is not being reflected. So the key thing here is that both the pitch and the orientation of the helix are key to what you see, key to the optical behavior. So in our cholesteric sheets, we typically make them like this. So you have a in the relaxed sheet, you have the helix being vertical, and then you stretch in one direction, and then because rubbers, like these elastomers are rubbers, they have Poisson's ratio of about 0.5. That means that basically all the volume is basically conserved. So as you make it longer, as you make the sheet longer in one direction, it has to get thinner in the perpendicular direction. And that means that the pitch is compressing, and therefore you get a shorter pitch, and you get a reduction of the helix, and therefore a blue shift of the color. So as I mentioned, the orientation of the helix is very important. So Lawrence, in his work that I showed before, they used cells. So they had cells with alignment layers, and this works very nice. That's how they could pattern these the sheets very nicely and so on. But it has some problems, some drawbacks. First of all, you can't make the CLCE any thickness because the influence from the surfaces has a limited range. Then, of course, for every film you make, you need a cell, and that's a sacrificial cell. You break it up, you lose it afterwards. So especially if you want to make a lot of sheets that should be large, this is maybe not a very scalable process. And finally, of course, when you open the cell to take out the film, it might tear. So you never know. Now, quite a while ago, Heino Finkelmann, who was really one of the pioneers of liquid crystal elastomers, he came up with another alternative for aligning the helix that he called anisotropic deswelling. So the idea here is that you have a solvent dissolved precursor, and you let the solvent evaporate while you're centrifuging. In this case, it was centrifuging. So instead of having isotropic shrinking, you have anisotropic shrinking. It only shrinks in one direction, and this aligns the helix. And maybe you have seen this paper they made a cholesteric liquid crystal laser that they could tune the color of by stretching. So this is a quite beautiful example of how nicely this works. The thing is that if you look at the papers, the principle of how this works is actually not completely trivial. At least maybe Heino is so smart, so for him it was trivial. For me it wasn't. So it took me a while to understand how this actually works. And it wasn't me who understood it, it was Bruno Furka-Petersic in a paper about cellulose nanocrystal suspensions that finally explained this. And it's a quite similar situation. For those, at least I know that there's one person here working with cellulose nanocrystal suspensions. It's again a cholesteric. It's a suspension. In this case, you have water as a solvent. You put a droplet, and you let the water evaporate. And as the water evaporates, it compresses the droplet and aligns the helix. And what Bruno explained is why this happens. So if the blue here is the solvent, as the solvent evaporates, but only in one direction, mind you, the director is basically the molecules are being pushed along the surface. So they are being aligned parallel to the subtone, being compressed like this, and you get a reduction of helix pitch. But what is not so obvious is, how is the helix aligned? So in fact, I thought I'm going to ask you to see if you figured this out. So to make it simple, I give you three options. So is it aligned like this, like the green arrow here? Is it aligned like the red arrow here, vertically? or is it not defined at all? So I'll give you 20 seconds to discuss with your neighbor. What do you think? And then I'll ask you. Okay? Okay, 20 seconds up. So we'll do it simple. I'll just ask 1, 2, 3, and then you shout green, red, or not defined, depending on what you think. Okay? And we'll see what I hear most. 1, 2, 3.
Green.
I heard all 3, but I think green was dominating. So we do it once more. 1, 2, 3.
Red.
Okay, there were some red people being strong enough, but I still hear the green. So anyway, it's obviously not obvious, which is what I want to illustrate here. The real result is red. It is vertical. And the reason that it's very easy to think green is that the helix doesn't exist. The thing is that when you draw the helix axis, you're actually drawing something that doesn't exist. The helix, as I told you before, is defined by being perpendicular to the director. And when we draw one helix like this, we are forgetting the continuum. There is, of course, many other molecules in the system, right? So that's where the helix is now. So this is the reason why anisotropic deswelling aligns the helix vertically, and it compresses the helix. So you get a shortening, and you get an alignment. So it's very powerful, very simple system. And as I said, this was made with this paper was published to explain cellulose nanocrystal suspension, but the physics is the same. So how do you do anisotropic deswelling then? So this is Finkelman's approach. You use a two-stage reaction. So you have first one network being formed, and then you let this solvent evaporate, and then you crosslink a second network. You fill your precursor solution into a vial, and you centrifuge it for many hours, 5 to 8 hours, at high temperature to make sure that the solvent evaporates. And during this time, the sample will shrink, and it can only do so in one direction because you are centrifuging the vial, and this is what gives you the anisotropic deswelling. So it works very nicely, but very complicated. And when we started working on this, and Vijay prepared his samples, we were really surprised that you don't need centrifugation. It works very easily. You just pour your solution on a dish. Here it's a dish with walls, but you don't actually need that. You can put it on any surface. And it doesn't deswell isotropically. It is actually pinned to the surface. So the key thing is really pinning to the surface to avoid that you can have shrinkage in the lateral dimension, and then you get this type of behavior. So we were wondering why, and we were thinking that maybe it's the two-stage crosslinking, because also we had a PETMP crosslinker initially that formed the first network, and then we formed a second network by photo crosslinking. But later we saw that we can do this also with oligomers. So there is no covalent network to begin with, and it still works well. So right now, I think the key thing is pinning to the substrate. That is that the droplet cannot shrink. That's the most important. And another interesting approach with this that you don't need to do the centrifugation and so on is that you can actually evaporate in both directions. So if you look at the papers on anisotropic deswelling, they always show the substrate from the top. So nice, colorful, like this, but if you look at the bottom, it looks like this. Because downwards, if you have glass, you don't have any deswelling in that direction. So the helix isn't aligned. So what we did now is we simply put it on a PDMS surface instead, and PDMS is porous, it soaks up the solvent, and now you have anisotropic deswelling in both directions, and you get very good color from both sides. And in fact, much more uniform. This is two films. The top one was made like this on PDMS. You see it's a bit more than 2 millimeters thick. I stress that, millimeters. And it's transparent and colorful. Normally, a liquid crystal that is 2 millimeters scatters like crazy. The lower one was only 0.6 millimeters, but it was evaporated on glass, and so it scatters much more. And you also see that here, that this is the spectrometer results of these two, and the one that was evaporated on PDMS has much higher transmittance and slightly blue-shifted peak. This is the reflection peak. And that's of course simply because this is one on glass. The anisotropic deswelling is more efficient here because it's deswelling in both directions. So you have stronger compression and therefore a shorter helix. And a big question, of course, if you want to use this is, well, is it quantitative? So we mounted a strain gauge to a CLC film, and we stretched it while measuring the force, and you can see it's changing color. And if you plot the data, this is just so you understand what you're seeing. This is the engineering strain on the bottom. So the first element of the strain tensor, DUXDX, or the extension along the direction that you're straining. And as you can see, it follows quite well the square root law that is what you expect to the simplest case of rubber, both for right-handed and left-handed polarization, and this is repeatable. So you can really directly relate the color to the strain. And if you look at the polarization, that's also quite interesting. Remember I said before that the cholesteric reflects the same handedness of polarization as the helix. And here you see that this is indeed how it starts out. There is no left-handed because this is a right-handed helix and only right-handed polarization. But then as you strain more, first you get an increase, which is probably because the helix is better aligned, but you also see that the left-handed is coming up. And that is because you're distorting the helix. It's no longer a perfectly sinusoidal modulation, it's being distorted, and so it's no longer just right-handed or left-handed. And you can also relate the strain to the stress, and this is typical two-step behavior. This is probably only distortion, and from this moment on you're starting to unwind the helix. So definitely you can use this quantitatively. And now recently we also found that you can make threads with the oligomer version of this, and you can see here it's very easy to pull these threads, and we can make them then in much longer versions. And this is the movie I showed at the beginning. This is in the polarized microscope in reflection mode, and under control stretching, and you see that it goes all the way from red to blue eventually, and it comes back very nicely when you relax it. This is a macroscopic movie where you see two threads on a black background, and you can see that this is 2 times real time, so a little bit faster than real time. And same thing here, this is also on a white background. Most work on cholesterics have a black background. In this case, you see the color even on a white background, which is quite unusual. And here we have woven these threads into a kind of simple weave that we are stretching to the left and then stretching to the right, and you see that the color change really reflects how you are stretching it. So you're really getting a 2D strain pattern that depends on how you're stretching it. And I got to use my old training from school time and tried sewing this into a stretchy black cloth, and it works quite nicely. We sewed L and E in regular yarn, and then the C with the elastomer, and you can see then that the C is really changing its color as you stretch it. Another interesting thing is the stitch length impacts the color. So here there are just 3 stitches. They go from long stitch length, from short stitch length on the left to long on the right. And this is a relaxed state where it's all a pinkish red kind of. And you see that it's the same material, but it goes violet on the right, and blue, and then green towards the left. So and that's simply because the longer the stitch length, the greater the strain in the actual fiber. And of course, another interesting thing is that here the initial color isn't red. In the microscope it was red, but in macroscopic fiber. This one is quite thick. It's more a pinkish white. But it becomes green when you stretch it. So why is this? Well, again, it's anisotropic deswelling. It's exactly the same thing. So in this fairly thick thread, the helix orientation isn't perfect. But just like with deswelling, you get the compression, in this case, by stretching. So in this case, because it's a rubber, you get compression along the perpendicular direction, and that aligns your helix, and that's why the color gets more intense as you stretch. So again, the whole thing, the model was developed for a very different system, but the physics is the same. And as I mentioned, you can run this through the washing machine. This is after 40-degree laundry in my regular washing machine at home, and it works perfectly well, so it survives without any problem. The question again, is this quantitative? And the answer is yes. This is, here we have the reflection wavelength versus strain, and here on the right side is the stress versus strain. And on the left side you see how the spectra change. So the intensity goes up, which is probably because we're aligning the helix better as we're straining, and then it goes down, because then you are starting to unwind the helix. But the important thing is that you have very quantitative behavior, and this is the fit where we also looked a little bit more careful at Eugene Terentiev's work, and you don't actually expect exactly a square root behavior. That's slightly different from cholesteric elastomers. So to end, how can we use these threads? Well, if you can sew them into garments, or you can weave them into garments, into fabrics, then obviously smart fabrics is an important potential market. And the first thing we are thinking of is compression stockings. My father needs compression stockings. He has serious arthritis and many other problems, and many people in his generation need this. And it can be quite tricky to judge when is the stocking appropriately, when is the pressure appropriate. So it could be very nice to have stockings where you can immediately see from the color whether the pressure is correct. And of course, there are many things you can do in clothes we wear, but textiles are actually all around us. So it's not just what you're wearing, but what you're sitting on. You have maybe a bag where you lift it and you can immediately see how heavy it is, for instance, could be useful at airports. You have your curtains, you have your carpets, and so on. And then outside your house, of course, you have a lot of things for sports, sailing boats, maybe you do paragliding, and in general, anything with a rope could be very, very interesting to have these types of threads integrated, because they indicate when the rope is about to burst. And of course, also in tires, you have textile threads, so there are many opportunities. And finally, going back to the structural health monitoring, the threads are very useful also there, of course, because the displacement transducer could, of course, be very nicely made using these threads. So, to conclude, I hope I could convince you that cholesteric crystal elastomers are interesting and have useful behavior because of their mechanochromic response, whether in threads or in sheets. And we can align the helix in these sheets and in the threads using anisotropic deswelling. And this is, because it's so simple, it's really something that can be scalable to industrial production levels. And I think there is really enormous potential in using cholesteric crystal elastomers for structural health monitoring, wearable technology, very many other aspects where you would like to have a color mechanochromic response in a textile. So I'll leave you with these two papers. The threads is still in review. I cannot just give you that, unfortunately. But the sheet is published in this left paper, and the right paper is on kind of various applications of the liquid crystal elastomers in the built environment, if you're interested in that. So with that, I thank you very much for your attention, and I'll be very happy to answer any questions you may have.
Okay, thank you very much for the very enlightening talk. Time for some questions. it's a very nice idea, but how have you dealt with the problem of temperature? Because temperature influences pitch while in high degree and can change the color sequence as well, or color.
Yeah, thank you. That's an important point, obviously. But these are liquid crystal elastomers. Once you cross-link them, the temperature dependence is very much reduced, if at all present. So you typically have a strong temperature dependence as a precursor, but once you have cross-linked them into a rubber, you can essentially get rid of the temperature dependence completely.
Okay, any other questions? Yes, there's one in the back.
I would like to know how they are better than fiber optics-based sensors.
Sorry, how much?
You mentioned that they are better than fiber optics-based sensors, fiber optic sensors. In which way? Because fibers can be able to pick up very tiny vibrations. If you monitor the polarization notice patterns, you can be able to pick small vibrations with fibers. So how are they better? In which way?
Would you mind taking off your face mask while asking the question? Sorry, I really have difficulty hearing.
Okay, so you mentioned that they're better than fiber optic sensors. And I was asking in which way are they better? Because you say that a sensor can be there and can be able to monitor a crack. And I'm thinking that if you monitor the polarization notice patterns, it can be able to detect the smallest vibrations. So how is that taking better?
Thank you very much, and also thank you for removing the face mask. Now I heard you perfectly. So I didn't necessarily mean that the liquid crystal elastomers are better than the fiber optic sensors. They are different. So they each have their pros and cons. And you're absolutely right. Where the fiber optic sensor... Is that mine? Where the fiber optic sensor measures, it measures with very high precision, very quickly. But the problem is that it measures locally. When you put in the sensor, it gives you one value. And the problem is that you can have a crack right next to it, and that crack is growing, but the sensor notices nothing, because where the sensor is, you have no response. So it's not, I'm not saying that they are better, I would say they're complementary, actually. So the idea is not to replace these sensors, but to add a 2D sensing system.
Okay, you have another question?
If the temperature doesn't affect the pitch, does it affect the stiffness of the elastomer and connects with the response?
That's a good point. Yes, temperature affects the elastic properties of rubbers. We haven't looked into it yet. What we have done is we have checked that the behavior doesn't change very much within, I think we just maybe checked between room temperature and 50 degrees Celsius or something like that. But it's a good point, we should do quantitative measurement as a function of temperature. Indeed, the elastic properties might need to be monitored. But of course, if once you know the behavior, then you can measure the temperature in conjunction with the sensor, and you can compensate for this.
Okay, yes?
And last question. I would like to ask you, have you studied time stability of that material? Just because if you will somehow apply this for buildings, winter tires, or some different application, you have to know that your material is stable and will show the same properties after a few weeks, few years, and so on.
Yeah, so that's a key thing that we're looking into now. What we have studied, first of all, is how is the behavior under strain. So at least, for instance, we put one of these sheets under strain for 24 hours and looked at it afterwards, and the color was identical, and as soon as the strain was removed, it relaxed immediately. So at least it's not, so creep is not an immediate problem, at least. The time stability over longer times is indeed an issue. So the ones that we have here that we published in the paper, they would not be useful in the long run, because their temperature is also an issue, because you have temperature variations. It's not just about the elastic properties, but you can have really, to some extent, phase separation going on here with temperature. So that's where what we are working on in the future is really optimizing the chemistry to ensure that we minimize these. But in the end, you might also need to reapply them after a year or something like that. But they should last at least a year, otherwise it's useless.
Okay, I think we have one more question, and I think we got.
Yes, thank you for your nice talk. I want just in the implementation, how many threads do you fabricate with the same color response? Yeah.
So can you see the beginning again?
Yeah, no, thanks for your nice talk. And how many threads did you fabricate with the same color response to the false?
How many threads? Well, so far the number is on the order of 10, I would say. We haven't done huge repetitions, but it seems very repeatable. We haven't really looked into it yet, but it works quite well.
Okay, so you had
Thank you very much.
questions. Let's thank our speaker again.